Okay, we're looking at problem number 81 on page 280 in the textbook. Worker efficiency. An efficiency study conducted for electronics showed that the number of Space Commander walkie-talkies assembled by the average worker T hours after starting work at 8 a.m. is given by. So they give us a function that models the number that an average worker can produce at time t. And this looks like a third-degree polynomial. And the domain there, t ranges from 0 to 4. And 0 is the 8 a.m. time beginning. And then 4 would be 12 noon. Okay, to answer the question at what time during the morning shift is the average worker performing at peak efficiency, I'm going to calculate the second derivative. So I'd have minus 6t plus 12. And to find critical points for it, I'm going to set it equal to 0. And see that t is equal to 2. So, and I know my domain is from 0 to 4. And let's see what happens here. At 1, the second derivative is positive. And at my test point, we'll use 3. The second derivative is negative. Now, what does the second derivative say about the first derivative say? What it says about the first derivative is that the first derivative is increasing, but the first derivative is the speed or rate at which the original function is changing. So the second derivative is like an acceleration. It's saying that the number of walkie-talkies being manufactured or assembled by the workers from 8 a.m. at 0 to 10 a.m. is accelerating. In other words, it's increasing at an accelerating rate. When people come in at 8 a.m., they start assembling these walkie-talkies and they get faster and better at it. But at 10 a.m., the second derivative changes to a negative, so that rate starts to slow down. And although the number of walkie-talkies being assembled is still increasing, it's not increasing quite as fast. That may indicate that at 10 o'clock it's time for a coffee break, that people are starting to maybe get tired or fatigued and starting to slow down their rate of assembly. It also says that the original function's graph is concave up from 8 a.m. to 10 a.m. and concave down from 10 to noon. So that's another indication that we have an inflection point, that the rate of change of the function is changing at the 10 a.m. mark. That people are coming in and starting up and accelerating their assembly, and then there's an inflection point, and the rate of change is starting to slow down, and the function becomes concave down. A real rough sketch of this function would be something like this, where there's an increasing rate up until 10 a.m. and then although the number assembled is still increasing, the rate has shifted and begins to slow down. So the peak time is 10 a.m. They're accelerating their rate of assembly up to 10 a.m. Before it starts to slow down, that's the fast time, right in the center of the graph in this case.